We are electrical and computer engineering students at Oregon State University.
We are Blue Team 1 of Spring 2019's Junior Design 2 class.
And we built a Bluetooth-operated AC switch.
I'm Trenton Kilgore. I worked on the hardware, the PCB design, and the documentation.
I'm Jordan Baxter. I worked on firmware development, enclosure design, expo display, video editing, and documentation.
My name is Soo-Young Liu, and I was responsible for writing the Android application, working on the expo poster, doing video recording, and video editing.
Our product is an AC wall-mountable device that features two independent outputs, both controlled remotely via Bluetooth. Along with this, we have an application that acts to turn on and off the device and features customizable timer settings.
Our project came with a few standardized requirements. It has to work with standard household lighting, it has to be easily controlled, it has to be safe, have an accurate timer, and have good range.
In addition to our standard requirements, we have a couple of custom requirements. First, our system must be wall-mounted and easily installed and removed. Second, we must have fully customizable timer settings.
Our project has several functional blocks: the relays, the current sense, the voltage rectifier, the microcontroller, firmware, and Bluetooth module, which are all on an Adafruit Feather, and our Android application. First, we will talk about the hardware block. This block consists of the PCB, or printed circuit board, and the electrical circuitry. It is powered off a 120 volt AC wall plug and consists of two branches. The first branch is our DC branch, which features the microcontroller, current sense, and control for the relays. The second branch is our AC branch, which features the pass-through side of the relays, the current sense, and finally our output. To better illustrate our hardware, here's a picture of our PCB. You can see our two branches, the AC side and the DC side, and in between them we have an isolation area. Along with this isolation area, our relay and our current sensor offer complete magnetic isolation from each branch.
Since our device is wall-mounted, special considerations had to be made for the enclosure. Namely, the mounting hole for the 3-prong connector, the mounting holes for the PCB, and leaving enough space for the outlets. Since all the weight of the device is going to be on the 3-prong plug, we had to put special structural supports around the 3-prong plug hole. In order to make this enclosure 3D printable, we had to make a couple of brackets separately from the enclosure. This is our outlet bracket, and this is our 3-prong plug input bracket. Here's an exploded rendering of our device. You can see the back panel, the two custom brackets, the PCB, the 3-prong NEMA connector, the outlets, and an acrylic front to see the device in operation. The firmware was written in Arduino, which is a combination of C and C++. It tracks outlet info using outlet classes, and it takes commands from and reports all information to the Android app. Here's our firmware block diagram. Our microcontroller takes info from the current sensors, tracks the outlets, on-off status, current info, and timer info in the outlet classes, builds outgoing data packets, sends them to the Bluetooth module, receives incoming data packets, sends them to the outlet classes, which then control the outlets. Here's a visual representation of our outgoing data packet. It's 20 bytes sent every half second and contains all the information about the outlet, including current, timer, and on-off data.
In order to control our device, we created an Android application. This app was written in Java using Android Studio and was designed to be easy to use. The app has separate on-off and timer settings and displays the current power draw of any devices that are connected. The device constantly updates the application and makes for easy user swapping. This diagram shows a high-level overview of how the app functions. After the app launches, the user can select a Bluetooth device to connect to. A Bluetooth UART service connects this device to the application and collects data and reports it back to the UI. As the user issues commands, these are translated into data packages, which are then sent back through our UART service to the device to tell it what to do. The app only sends out two types of data packets. The first one is an on-off command. This contains information such as an outlet identifier, which determines which outlet to control. The second is a timer data packet. This contains information such as which timer to switch on and off, as well as the timer value. Here are a few screenshots of our final application. From left to right, we have the device disconnected state, the left outlet on, a timer select dialog, and a timer cancel dialog. Here is a look at the completed Bluetooth switch. The entire enclosure is 3D printed, making for a solid and elegant solution to contain all the components. The assembly is easy to install and remove. In its default state, each outlet serves as an open AC pass-through. After connecting to the device using the Android app, the device will reset each outlet to its off state, and the user may now control each outlet individually. The power draw of each outlet is also displayed. The app allows the user to set timer settings using both hours and minutes. The timer is set separately for each outlet and can be disabled easily. Once a mobile device is disconnected, another user can easily connect with their phone and see all the settings that have been previously set. This design makes it easy for different users to connect and control the same device. As can be seen here, the settings set by the phone on the left have now been transferred over to the phone on the right. Because our device uses Bluetooth, it can also be operated at long distances.
What are some future improvements we could make to this device? Easiest would be improvements to the app software. Features such as an auto-connect function and data type recognition. Next would be firmware updates, such as interrupt-based commands and Bluetooth mesh. Finally, and most difficult to implement, would be hardware updates, such as resettable fuses, an integrated microcontroller, and a smaller 3-pronged plug.